Hey guys, welcome to Friction. This is the next unit of study we're looking at here, and friction is very familiar to us. We know how friction works. We know what it is. We're going to get to some really specific things about it. But without friction, we wouldn't be able to walk. We wouldn't be able to do any of that stuff. Lots of Newton's third laws wouldn't work. But we have a couple examples here. Sandpaper, anything against rough edges obviously creates more friction. And there's a couple of different types of friction that we'll talk about. We know we have air resistance. That is the resistance of the air, obviously. We have viscosity. And that's kind of like the thickness of fluid, like think honey versus water and oil, those kinds of things. So viscosity can be considered friction. And then we have rolling friction. That helps stop things. What we're going to be dealing with is static and kinetic friction. And those will be the main drivers of our conversations. And so where does friction come from? So we understand on a microscopic scale, most surfaces are rough. There's lots of complex interactions between them that we won't necessarily be considering now, but we model the force in a simple way. And so what we're doing here is we're looking at this and understanding that is what the surfaces look like when you zoom in. The first friction we're going to be looking at is kinetic friction. And that is if something is already in motion, so it's already moving, okay? The equation for sliding or kinetic friction looks something like this. I say F sub F equals mu sub K times Fn. And so that's a pretty interesting idea. The mu sub K is called the coefficient of kinetic friction. And so I have a chart here we'll look at here in a second. But the coefficient of kinetic friction is unique to specific surfaces. So once you establish the surfaces you're dealing with, it pretty much stays the same. The normal force is simply that. It's the normal force, and it can be the weight, but really it's just the normal force or the support force that we'll look at how that works here in a second. But here's my formula for it. FF equals mu times normal force, and the coefficient of kinetic friction is the mu, Fn is the normal force. And so I have this chart here, and these are established values for the most part. We have wood on wood, ice and ice, and there's a couple of interesting ones we want to look at. Metal on metal lubricated, that's 0.07, so that's not a lot. So think about the stuff in your motor. There's lots of oil when you're dealing with those things. That's kind of interesting. Here we have steel on steel unlubricated. That is magnitudes greater. And so a good example to think about that is train tracks, how trains work, subways, that kind of thing. Metal on metal is very frictionful, if you will. It has lots of coefficient of friction, so it's really tough to move. One that's really important for us is rubber on concrete, right? That's how we drive around. Rubber on wet concrete, so notice here it's a little less. So when the roads get wet, it's sometimes harder to stop. Doesn't happen too much for us. One that's really kind of interesting here is this human joints and limbs, that synovial fluid. It's at 0.01, and that's really useful to us. We like our joints to move easily. We don't like it when they get stuck. It's usually kind of painful there. But these are just established values, and we'll do a couple of labs where we'll find the coefficients of friction between that. So that's an interesting idea how that works. I want to go back to the normal force before we continue on. Remember, I have an object, change my pen here. I have an object represented by a box with a mass, and I have an FG that's always pointed down and a normal force that's always pointed up. That's pretty interesting. So when I'm thinking about this, if I increase the mass, I increase the weight of the object, which means this also increases. If I follow my formula, friction force is mu times the normal force. If my normal force goes up, that means my friction force goes up. I haven't changed mu. I didn't change what surfaces are involved here. That's that same idea as if we remember the normal force is like what the scale says. If I have my block again, and I have my FG, and then I'm going to write this in red over here. I have my normal force in red pointing up. And let's say for whatever reason, I somehow apply more force, like I push down on the object a bunch. What happens here, and let's assume the object still isn't accelerating. Net force would be 0. What happens here is the normal force is going to go up, and it's going to go up by how much I push down. So I can increase the amount of friction I have by pushing down, by smashing down. So a quick little example is, get your hand and slide it across the table or whatever you're looking at, and then smash down your hand really hard into the surface and see which one it's harder to move. We didn't change the type of surfaces. We didn't change the coefficient of friction. We just changed what the normal force is on the object. So that's a very interesting implication about how when we deal with friction, that changes a little bit. So we have a kinetic friction force example here. We're going to sketch the free body diagram first. So here's my mass. I have my FG that's always pointing down. My normal force will be pointing up. And I'm accelerating this, so I want to see the person going this way, and then I'm going to draw a tiny friction force going that way. Net force in the y direction should be 0. It's not accelerating off of the ground. So we'll kind of do it the long way here. Fn minus Fg is equal to 0. And yes, the normal force is equal to the weight in this case. That's what we expect. In the horizontal direction, though, we knew that the box was accelerated across. So in the x direction, there is some type of acceleration happening. The forces responsible for providing that are the person pulling it to the right, how we've drawn it, and the friction pointing to the left. When we sub those guys in, we have Fp minus Ff equals m times the acceleration. And something I kind of like to do is I like to take a look at my friction force and break it down one more level. I have Fp minus, I'm going to substitute all of that with mu times mg, which is my normal force. At this point right here, we have a really good idea of what we know and what we don't know. I can find mu, I can find mass, I can find acceleration, I can find the force of the push. So depending on what I'm given kind of dictates how difficult the question gets. So let's take a look at throwing a couple numbers into my example here. So on this one, it looks like I'm given the coefficient of kinetic friction as 0.4. The mass of the object is 3.2 kilograms, and I am asking what the force of friction is. So this is pretty straightforward. This is just asking me to do this. We don't know too much else the way the question is worded, but there's Fg, there's Fn, and it's sliding. I don't really know what else is happening to it, but the way this kind of question is worded, we just want to know what the force of friction is here. So that's why we're doing it this way. I do know, however, the force of the normal force is equal to Fg, which is equal to mg. Plug everything in. The force of friction is mu mg. So 0.4, 3.2, 9.8. So the force of friction here is about 12.5 newtons of friction force that would oppose the motion there. So not too bad for that guy. The next kinetic example is here. A 10 kilogram block is being pushed across the horizontal floor with a certain force, and it's accelerating, and we have to determine what the coefficient of friction is. So that's a bit more exciting here. So the first thing I want to do is I'm going to establish my free body diagram. I have Fg pointing down, Fn going up, some type of push going that way, and friction pointing to the left, always opposing motion. So it gave me some information here that I need to make sure I know. Here's my acceleration rate. There's my force. There's my mass. So that gives me lots of information. I know my normal force is equal to the weight. So I'm going to go ahead and chunk that in there. So let's see, 10 times 9.8. So the normal force for this question is going to be 98 newtons. Okay, cool. It looks like it's accelerating in the x direction. So I'm going to have Fp minus Ff is equal to ma. And so notice that's where my coefficient of friction is going to be hiding in there. So I'm going to go ahead and finish this out. The push minus the mu mg, or the normal force. I guess I can leave the normal force there since I already found it. Equals to ma. So notice we know all of this information, which allows us to throw that in there. So to finish this off, looks like the push is 60. This is 98. The mass is 10. And the acceleration is 0.4. A little bit of number crunching gives you a value of about 0.57. And something to remember, the coefficient of friction is a unitless ratio. Remember, the force of friction is mu times the normal force. When I solve for mu, something to remember is we have the units of Newton divided by Newton. Those cancel. So that's just a ratio between forces. That's what that coefficient of friction is. Most of the time, you're going to get a value less than 1. You're not going to have necessarily perfect friction forces. It's very possible to have something greater than 1. Different types of surfaces can yield to that. So think of Velcro. That's an interesting idea. We'll talk about that later. But typically, you get a value less than 1. All right, that's it for part 1. Part 2, we'll talk about static and its implication on how we solve these questions. Thanks, guys. Bye.